Today we're going to be talking about parallel programming models. First of all, we're going to define the three parallel programming models: shared address space, message passing, and data parallel. And then we'll be going into shared address space in a little bit more detail. We'll talk about it, and we'll talk about the way the processors are interconnected. Then we'll go to message passing and do the same thing. The first of our three parallel programming models is shared address space programming. And in shared address space programming, the processes are communicating through shared memory. So they're reading and writing shared variables. With message passing, there's no explicit shared memory. Rather, the processes are creating messages and sending them to other processes or other threads. The other threads are receiving them, and then they do something with that information. So communication between the processes is asynchronous. The process sends a message, and only sometimes later does another process receive it. Data parallel programming, on the other hand, has to do with the SIMD architectures we talked about on the first day. Here we have a single instruction operating on a lot of different pairs of data, a lot of different streams of data, usually two operands for each operation. And so you have a single instruction, but the single instruction is applied to a lot of different data, and that makes it easier. It saves time in sequencing through the instructions. It also saves some synchronization, as we'll see. But we're not going to be talking much about data parallel today. We'll talk about it a little bit further when we cover GPUs next week. Okay, well, regardless of the method we use, user-level primitives are provided to realize the programming model. That means that if we're doing shared memory programming, for example, we'll have locking mechanisms that will allow us to control access to shared data. And if we're doing message passing programming, we'll have send and receive implemented in the language or in the operating system. And back in the days, let's say back in the 1980s, when parallel programming really got its start, the kind of programming that you would use depended upon the kind of architecture you had. If you had a shared memory architecture, you'd choose shared memory programming. If you had an architecture without shared memory, then you'd have to pass messages. But those days are long past because shared memory programming is now supported on distributed memory architectures under the hood, so to speak. And message passing primitives are provided even for shared memory systems. Okay, so as far as we're concerned about shared address space programming, the salient fact is that we have a shared address space in the programming model, and that means that the processes can access the same memory locations. Communication is by means of loads and stores, and so what I mean is that the only way that processes can communicate is by storing a value of a variable, and then the other thread or the other process reads that value. That's convenient because when we have processes reading and writing variables, they're always reading and writing. The only difference in this case is that another thread or another process might be interested in what they write. And this supports a wide variety of granularities, a wide range of granularities. If you're talking about message passing programming, it takes time for the message to be created and sent and then received by the other process. So the time it takes to communicate is going to be much longer than it would necessarily be when you're doing shared memory programming. You can do shared memory programming where you're not trying to communicate real rapidly, but it can do a lot more rapid communication than message passing programming. And so when we do shared memory programming, we can communicate perhaps up to hundreds of other processors. You can't really communicate across the large range of architecture sizes that you can with message passing, because when you have architectures that are too large, it just gets too long to access memory in the most remote corners. So you'll normally be using message passing. But up to several hundred processors, you can do shared memory effectively. Now, a lot of times you'll hear people talk about shared memory programming, and this presumes that you actually have a shared memory. But as we've said, since the late 1980s, there have been shared memory type of programming supported on architectures that don't have a common memory. So what matters nowadays is not that you have the shared memory, but that you program as if you did, and that's what the textbook calls shared address space programming. So when we return the next time, we'll be talking about the shared address space model.